Our galaxy is called the Milky Way. We often think of it as a faint band of light across the sky that can be seen from dark locations. That band can be either an outer arm of the Milky Way or toward the galaxy's center, depending on the time of year. But the Milky Way isn't just that stripe in the sky. Almost everything we can see in the night sky belongs to the Milky Way, even if it isn't along that band. Our Milky Way seems to be a spiral-shaped galaxy, similar to Andromeda pictured on the right. Andromeda is the closest large galaxy to our own. When we look towards Orion, seen in the sky map, a lighter strip showing us the location of one of the Milky Way's spiral arms. This is a composite image showing what the Milky Way looks like in the direction of the galactic center. This is not the entire galaxy, and a photo of the entire galaxy does not exist. It would be impossible for us to take a photo of the entire galaxy from inside the galaxy. Notice the brighter area in the center. That's the galaxy's core or nucleus. It's mostly obscured, though, by dark bands of dust between our location and the core. Light cannot penetrate through this dust, so we see just darkness. Again, this is the Andromeda galaxy, not the Milky Way. You can see two of Andromeda's satellite galaxies also included in this photo. If this were the Milky Way, though, our solar system's location would be indicated by this arrow, far out from the center of the galaxy, out in one of the spiral arms. To describe the Milky Way, perhaps the easiest way to think of it is to imagine a fried egg. The bulge in the middle, the yolk, would represent the galactic core, while the white part would represent a relatively flattened disk where the arms are. However, unlike the egg white, the galaxy's flattened disk is not solid from edge to edge. There's a lot of empty space between the stars and even between the arms. The galaxy is huge, about 100,000 light years in diameter and between 1 and 3,000 light years thick. If the sun were the size of a period at the end of the sentence on your paper, the Milky Way galaxy would be the size of the entire United States. As I mentioned, we can't take a picture of the entire Milky Way from inside it. But if we wanted to shoot a picture from the outside, we'd have to be able to get a spacecraft above the plane of the Milky Way to a height equal to our distance from the galactic center. How long would it take to get there? Well, first, let's imagine we have a spacecraft that can travel at the speed of light, 186,282 miles per second. What do you think it would take? 2 months? 5 years? 250 years? 30,000 years? Or 5 million years? Take a moment and make a guess. The sun is about 8,500 parsecs, or 30,000 years from the galactic center, and that's traveling at the speed of light. New Horizons, the fastest spacecraft launched, traveled at about 10 miles per second. To travel 30,000 light years, or 1.8 times 10 to the 17th power miles, the New Horizons spacecraft would take 570 million years to get there to snap a photo. No battery could last that long. Voyager 1 is the most distant spacecraft from Earth. It and its twin were launched in 1977 and have barely reached the edge of our solar system. Voyager 1 entered the area considered to be interstellar space in August of 2012, while Voyager 2 just left our solar system in December of 2018. These spacecraft have been traveling for over 40 years, and they're still basically in our cosmic backyard. Here are a few images of some galaxies that look pretty similar to what we think the Milky Way looks like. We think it's roughly 100,000 light years across and has between 100 and 400 billion stars. That's a pretty wide range, but it's hard to narrow down since the light from many of these stars is completely invisible to us here on Earth, blocked by the large amounts of dust in the galaxy. Just like the planets orbiting around the Sun, our Sun orbits the center of the Milky Way. It takes about 250 million years for our Sun to travel its path around the galaxy. So the last time our solar system was in this area of space, dinosaurs were just getting started on this planet. Here is another spiral galaxy, similar to the Milky Way, seen from two different views. The first image shows it face on, with the spiral arms visible within the stellar disk. The second picture shows the galaxy edge on, meaning that you're looking at it from the side. Here, you can more easily see the dust lane, a thin, patchy disk of gas and dust that is fuel for the next generation of stars. For the Milky Way and other spiral galaxies, there are three major areas of the galaxy. Here you see an illustration of a spiral, both face-on and edge-on. The nuclear bulge is what we call the galactic center. It's in the middle, like the nucleus of an atom or a cell, and it bulges out thicker than the rest of the galaxy. Then, moving farther out, you can see the stellar disk. This is where the spiral arms live, and this would be the white part in our egg model. Surrounding the entire disk is an area called the halo. It isn't visible in the upper image, but it's an area both above and below the plane of the rest of the galaxies, where fewer stars exist, and is populated by groups of stars called globular clusters. Here's another image of the same information. The galactic bulge surrounds the galactic center, and this bulge is home to mostly older stars. Moving outward is the galactic disk, full of gas and dust, called the interstellar medium, or ISM, and the spiral arms. Though there are old stars here too, the gas and dust in this region means that we also find young stars here. Another type of star cluster, called open clusters, live within the galactic disk. The galactic halo surrounds everything and is home to the globular clusters and other very old stars. In the bottom images, you can see the differences between the two types of clusters. Open clusters are dense collections of stars. However, can you see that in this globular cluster, we have many more stars that are even more closely packed together? Globular clusters are very old, and they almost look like mini galaxies. In fact, some of them may be the remnant cores of galaxies that got consumed by their parent galaxy. There are three different populations or types of stars. Population 3 stars are the oldest types of stars that would have existed shortly after the Big Bang, consisting only of hydrogen and helium. They don't appear in the graphic as no more stars of this type exist. They all died long ago. Population 2, sometimes just called Pop2 stars, are the older stars. These are called metal-poor stars, meaning that they have only very small amounts of material other than hydrogen and helium in them. Even though there are a lot more nonmetals beyond hydrogen and helium, astronomers call anything heavier than helium a metal. These stars are typically found in the nuclear bulge, the galactic halo, and in globular clusters. These stars are typically redder in color and are cooler stars. Population 1 or Pop1 stars are much younger than their Pop2 cousins. They are located mostly in the spiral arms and in the galactic disk. They burn, on average, much hotter and bluer than the Pop2 stars. Our Sun is a population 1 star. Compare the two line spectra at the top of the screen. A Pop2 spectrum is on top and a Pop1 star spectrum is on the bottom. Notice that the Pop2 spectrum only has a few strong lines. These are basically just the hydrogen lines. There isn't much else in a POP2 star. But the POP1 spectrum has a few other noticeable lines in them coming from the heavier metal elements. You see a similar diagram below. This time, the POP2 diagram is on the bottom, showing very few features. But the upper curve shows a lot more activity, as POP1 stars contain many more of these heavier elements. Young stars contain more metals than older stars. These two graphs show elemental abundance, or how much there is of different elements in space. The second graph is on a linear scale. Notice that only hydrogen and helium show up as having much presence at all. And though carbon, nitrogen, oxygen, and iron show up as tiny blips on the bottom axis, nothing much else shows up. The graph on the left uses a logarithmic scale, similar to the HR diagram, where we can spread out the data a little more to show a lot more elements. Notice the zigzag pattern and how the even-numbered elements are much more common than the odd-numbered elements. This also shows just how much more abundant hydrogen and helium are than the other elements, over 2 orders of magnitude, or 2 exponents, higher than the others. Again, much of what we believe to be true about our galaxy is speculation. We know more about other galaxies than we do about our own. The structure of the Milky Way is difficult to determine, not only because we are inside of it, but because it's difficult to obtain precise distance measurements and that our view of much of the galaxy is blocked by gas and dust. William Herschel, the astronomer who discovered the planet Uranus, made the first attempt to sketch out the appearance of the Milky Way. He thought the sun was relatively close to the center, and the other stars were relatively evenly spaced around it, similar to a grindstone shape with the sun in the middle. This was far from the truth, though, for a couple of reasons. Number one, Herschel assumed that all stars were identical, each giving off the same amount of light. So he assumed that he could determine distance just by looking at how bright a star was. The other problem was that he didn't know about what is called interstellar extinction, our inability to see objects that are on the other side of dark dust clouds. Here's a photo that more clearly shows interstellar extinction. Herschel assumed that we were the center of the galaxy because he couldn't see any other clear center. In this image, the true center of the galaxy is circled. It doesn't look special, though, because dark nebulae and dust obscure our view. This interstellar extinction blocks out all of the stars that are very far away from the sun. So how can we know where the center is if we can't see very far in that direction? Think about driving through fog. A thin layer of fog makes it difficult to see very far in front of you horizontally, but you can still easily see distant objects that are above the fog layer. Though we can't see through the galaxy to the center, we can see globular clusters that group up above the galactic center. With just a little bit of geometry, we can actually determine how far away the center of the galaxy must be. We have several ways to discern the structure of the Milky Way from what we can see, even though there is much we cannot see. As with the globular clusters, we can select bright objects that are visible to determine their distance and how they are moving. Another major way is using wavelengths of light other than just visible light. Interstellar extinction makes us unable to view the galactic center in the visible light, but it is very clearly visible if we use other parts of the spectrum. We will look at this more closely momentarily. Finally, we can look at how quickly other objects are moving relative to our position, and we can determine mass distributions throughout our galaxy based on gravitational interactions between objects. You might be wondering how we can measure distances to these far-off objects. We've talked about the parallax method before, but that only works for objects that are relatively close to us. We need to be able to measure distance accurately to much farther off objects, as the Milky Way is huge, 100,000 light years across. There are a couple of easy ways, one using variable stars, but Herschel didn't know about these methods in his time. Take a look at this set of images. Can you see how the star dims over time, brightens back to its original luminosity, and then begins to dim again? The rate at which this dimming and brightening occurs can help us determine distance. One major way we can determine distance to far-off objects is by using a type of variable star called a Cepheid variable. We'll talk about these more in the next lecture, but these pulsating stars were discovered by American astronomer Henrietta Swan Leavitt, and she realized that the brightness of these stars varies over time in a very regular way. Notice the two graphs on the right. The first star goes through about 5 cycles in 3 days, while the second star goes through 3 cycles in 9 days. Leavitt realized that the time period was directly proportional to the star's luminosity. That means knowing the brightness of the star from Earth and the star's true luminosity from its pulsation rate, we can calculate the distance to that star. Now remember, there are 2 different types of clusters. These more spread out, younger clusters called open clusters, and the more densely compacted, older globular clusters that live in the galactic halo. Here's another image of a globular cluster. They can contain up to 1 million stars, and they are very old, about 11 billion years old. The entire universe is less than 14 billion years old. There are about 200 of these clusters that surround our Milky Way. Harlow Shapley, another American astronomer, noticed that though globular clusters can be seen in all directions, the vast majority of them are on one side of the sky, in the direction of the galactic center. They are more heavily concentrated there because the clusters, like everything else in the galaxy, orbit the galactic center. Globular clusters have lots of Cepheid variable stars, and he used their pulsation rates to determine distance to the galactic center. I said that in the direction of the galactic center, we can see very little visible light due to gas and dust that blocks that wavelength of light. Only 1 out of 10 to the 12th, or 1 out of 1 trillion optical photons, makes it out through this dust. Since the light can't penetrate the dust, it gets scattered. Since blue light is scattered more, we see less of it. Earth has a blue sky because of the scattering of blue light. Red light is transmitted easiest, so stars we see through dust look redder than they really are. So we don't get a very accurate picture of what we're looking at. So what are the alternatives? Remember, visible light, the type of light that we can see, is only a tiny bit of all the available light produced by stars. Each type of light, from radio through gamma, has different capabilities regarding penetration through dust clouds. Here are 10 different images of the same area of sky, looking toward the Milky Way's center. Notice that the third from the bottom, there's a lot of dust and not much to see. This is the optical wavelengths, meaning visible light. Notice how we see a whole lot more detail in each of the other areas of the spectrum, whether longer or shorter wavelengths. Now let's look at 2 different types of infrared radiation. The near infrared image shows us the very clearly seen nuclear bulge. You can still see a bit of the dust lane in front of it, but the full galactic plane is visible. You can also see the two Magellanic Clouds below the disk. These are a couple of small satellite galaxies that orbit the Milky Way. In the far infrared image at the bottom, you can see even more detail, as this wavelength of light is barely absorbed by dust at all. Here are a couple more spiral galaxies that probably look similar to our own. The Sombrero Galaxy we see edge on. Though we can't see the spiral arms, we can see the gas and dust lane around the outside. NGC 2997 is a face-on spiral, and we can see its dust lanes as dark lines between and within the spiral arms. Here is the Milky Way as seen in radio light. The dust that so easily blocks visible light doesn't block radio wave transmission at all. We can clearly see in any direction using radio wavelength light. You can see that the area most active in the radio part of the spectrum coincides with the galactic disk's plane. That should make sense, since there are so many stars here and many fewer in the galactic halo. There are a couple of side-by-side images also taken of the galactic center. In the first image, we see an optical, visible light image. Lots of dark dust blocks out where the actual center of the galaxy is. In radio waves, however, that extremely bright spot on the right is readily recognizable. A specific wavelength of radio waves, the 21 centimeter waves, shows us locations of neutral hydrogen clouds. We can use the Doppler effect to determine the distance to these clouds in the spiral arms. Notice that there is a blank area in the bottom of this image. We can't see what's going on in the arms back there, as that area is behind the galaxy center. There are structures in the centers of most, if not all, large galaxies called supermassive black holes. The types of black holes we talked about in Unit 3 may have a mass 10 times heavier than the Sun. These are hundreds of thousands or millions of times heavier. This is an image showing several stars that are nearest our galaxy's black hole. They orbit the black hole in much the same way as the Earth orbits the Sun. Go through the PowerPoint in slideshow mode and activate this link to see these stars closest to the galactic center orbiting what appears to be nothing. You can tell that these stars are orbiting something, but when you zoom in, they don't appear to be circling around anything at all. The object in the center of our galaxy is a supermassive black hole. The name of the Milky Way's supermassive black hole is Sagittarius A star, and it's abbreviated like this. The name Sagittarius is in it since the black hole is in the direction of the constellation of Sagittarius. You can see the area around the black hole here as imaged in radio waves. Look at just how active the black hole is in radio wavelengths. Zoomed in, you can see arcs of material coming out from the center as other objects are gravitationally disrupted by this beast. Using a system of telescopes called the Event Horizon Telescope, we have now imaged the supermassive black holes in the center of two different galaxies. First, the one in galaxy M87, then Sagittarius A star in our own Milky Way. Here is the galactic center, this time imaged with X-rays. Though you see a bright area in the center, active in the X-ray part of the spectrum, many supermassive black holes in other galaxies are even more active in this part of the spectrum. Orbital paths taken by Milky Way objects depend on where in the galaxy they are located. For objects in the galactic plane, Within the galaxy's disk, these stars have elliptical but nearly circular orbits and revolve within the plane of the disk. These stars orbit the galaxy nucleus in much the same way as the planets in our solar system orbit the sun. However, objects located within the galactic halo have much more inclined, randomly oriented orbits. This is similar to Oort cloud objects within our solar system that can orbit the sun coming from any direction. Think back to when we talked about planet revolution times. We talked about the fact that Mercury was the fastest planet, not just because it follows a smaller orbital path around the sun, but that it also travels at a faster rate of speed. Revolution in our galaxy is the same. Our sun orbits the galactic center at a speed of about 220 kilometers per second, and it takes about 250 million years to complete a full orbit. However, this is not true of all stars. Stars located closer into the center of the galaxy actually orbit faster, and the stars farther from the nucleus travel more slowly. But though the distant stars orbit more slowly than the ones closer in, they are still traveling way faster than they should be. These outer stars are traveling so rapidly that the whole galaxy should be flinging itself apart. Imagine you have a pile of sand on top of a plate and you spin around really fast. The sand would fly out away from you all over the place. The galaxy doesn't seem to have enough mass to provide enough gravity for it to hold itself together. Our best estimate about the mass of the entire Milky Way, based on rotational speed, is about 1 billion solar masses within the disk and 1 trillion solar masses if we include the material in the halo. However, when we sum up all the individual objects we can measure, it turns out that we are missing a lot of mass. We aren't sure why the numbers are so far off from what we would expect. It is thought that maybe there is a large amount of something called dark matter out there that is providing enough gravity for the galaxy to hold on to those super fast outer stars. Vera Rubin was the first scientist to realize this discrepancy. She realized that there must be a lot more matter in the galaxy than what we can see. In fact, galaxies appear to be mostly made of this material we now call dark matter. This missing matter is called dark matter. Number one, because we can't see it. It's dark, not reflecting light towards us. However, it must provide mass, and thus gravity, to the galaxy because we can see the effect of the gravity on the galaxy's rotation rate. We really don't know what the nature of the material is beyond that. Maybe it's normal everyday matter, just in a form that it emits so little light that we cannot see it, perhaps in the form of very dim stars or little black holes. More likely, though, it may be different types of particles we may not even understand yet. Let's look at a few possibilities. One type of particle that may contribute to this missing mass is called the neutrino. These are low-mass particles that are produced in stars as they undergo fusion. These are very common particles produced in all active stars, but they are also so lightweight that they probably cannot account for more than a few % of dark matter. Another option is a group of particles called WIMPs, or weakly interacting massive particles. We haven't ever discovered these particles, but they're a type of particle that is predicted to exist. Particle accelerators like the Large Hadron Collider are searching for the existence of this type of particle, but experiments have been unsuccessful so far. A third dark matter possibility is a type of object called a macho. Machos are not particles, but are different types of objects that are very heavy but small and thus hard to detect. We aren't sure whether any or all of these may contribute to the mass we think the Milky Way has, but we cannot see. Some scientists wonder whether dark matter really exists at all. So, does dark matter exist? The fact is, we aren't sure. Either it does exist, and we really are observing the effects of its gravitational attraction, even though we can't see the material itself and don't yet have the technology to detect it, or maybe there's just something else that we are misunderstanding, making us believe that this matter is out there when it really isn't. A lot of research is currently being conducted in the area of dark matter and another similar topic, dark energy. In the coming years, we'll probably understand what's going on much more clearly.